Okay, well, it's a pleasure to introduce an old friend of mine. I was here about 3 years when they brought this young fella down from Stony Brook. He seemed to have a pretty good head on his shoulders, and I was an experimentalist and he was a theorist. So we got along fine. I could fill notebooks with the amount of physics that this guy taught me. Just in casual conversation and so forth. And he later became quite expert in computers and computation. And I guess he's going to tell us a lot about that. But Johnson originally came from Vanderbilt on into Stony Brook, got his PhD there, and then came directly on our faculty. And he's a wizard of a teacher. He has, sometimes he blows the students away, at least when he teaches in the 200 level, because that's what he learned at Vanderbilt, so he might as well learn it here. We had a long friendship, 41 years, and it's a pleasure to introduce him, and I certainly hope that because they're going to give him a 40-year pin in a ceremony upcoming and officially retire him, that he doesn't go very far from here. But since he owns a home locally, and here's our seminar chairman who should be doing this job, but that's quite all right.
My students help me know.
But anyway, I did a fairly credible job in your stead. Joe, let's hear about 40 years.
I have actually, I took this back about 10 more years, so it's actually 50 years. I'm talking about, I guess you would say, I started 1959. That was the year I took a course in Eisenhardt's book on differential geometry and Riemannian geometry. And that's hard enough to constitute research, I think. So it actually goes back 50 years, and I have 50 slides exactly, so you can count them. And I have to do one slide a minute, which is 1 year a minute. So at some point in your life, imagine that you describe your life as 1 minute for every year that existed in your adult life. And so that's what I'll be doing. I made a special pact with Pavel. I don't see him, not to ask any questions until the end, so I can keep a really good pace.
The only way you can do it is to stay away.
What I have here is I have a challenge for all of you. And I will use some notes here because it will keep me on track and I won't just wander and take up too much time. I challenge each of you at the end of your formal part of your career to give a colloquium that covers your research. I'm talking to the faculty here. Not the research of coworkers, not the research advances in your field, and not the reminiscences of time past. You'll find that I've essentially mentioned no one here. Let's bind them in a paper form, which I've done here. These are my main papers and this presentation right here, and patents and other things, and present them to the department, and it's being videotaped. So I'll make a DVD of that, and if we archive that for every faculty member that went through, think how nice it'd be. Think how nice it'd be if Yakir Haranov had done this when he got ready to leave, and Frank had done it. We could go in there and have a composite 1 hour presentation.
I'm still here.
I know you're still here. That's why I'm kind of saying it's time for you to do this, Frank. So anyway, that's what this is going to be. I'm going to give up that word that we all used. We did this and we did that, meaning the entirety of all scientists in the world. And I will talk about what I did, my personal premises and so forth. My personal premise is that science is the study of information. It's really what I'm going to be talking about today are observables that are in physics. And if something can't be measured or observed, its existence is meaningless. And that seems very logical, but I think you'll see that it has some serious consequences. We should really be very cautious when we base our scientific theory on something that doesn't exist. Well, let's just start with something really fundamental, and we'll be using again and again. Let me redefine, I think everybody here knows this, a linear vector space. Linear vector space in n dimensions is a set of objects which has addition defined and multiplication by a scalar, and usually a basis so that we can expand any one of those vectors as a set of other vectors. I've used Dirac notation there. Now, a metric space is a linear vector space with a symmetric product. And that product is normally known as a scalar product. We can put decomposition of unity in the middle and expand this And we also know that it's the magnitude of A times the magnitude of B times the cosine of the angle. What that means is once we can do the scalar product, multiply all the components together, we can find the length of any vector by multiplying it by itself and taking the square root. And we can find the angle between any two. This is true in 3 dimensions, in 12 dimensions, in 70 dimensions, infinite number of dimensions like in a Hilbert space, like we do in quantum theory. And this is the critical thing. If these are unit vectors, of course, what we get are the cosines of the angles, which are the things that we use in quantum theory when we project psi onto phi. Now I wanted to talk about what a Lie algebra is, because almost all of what I do today will be talking about Lie algebras and related things. A Lie algebra is a linear vector space with an antisymmetric product, as opposed to a symmetric product. And I'll try not to do this, which always makes me nauseous. You ever notice how people do that when they talk about things? I'll try not to do that. The Lie algebra is defined with a product which says that for any two basis elements, I and j, there's a linear combination of other elements in the vector space such that this closes, and therefore the commutator, as we call it, of two things is equal to another thing. But it's not a commutator here. It's not a commutator of matrices, and they're not matrices until you find what is called a representation of that Lie algebra. It also has to obey the Jacobi identity. That means the commutator of the commutator of the commutator of the cyclic permutations gives you 0. Now, this thing generates a Lie group when we exponentiate it. And that's the incredible thing. If we take a Lie algebra and exponentiate one of those elements with a parameter, it expands. And we normally will write any general element as a linear combination of the basis elements for the space. What is classical physics? Classical physics is a study of a particle that moves in 3 dimensions, or maybe it's even in phase space, with 6 dimensions, 3 position, 3 momenta, or maybe we have 70 particles in 6 times 70 dimensions. Still, it's a vector. Maybe it's 70 particles moving, as Frank would do, in a nucleus, and looking at this in quantum theory. It's still in a Hilbert space. All of these things, and this will come out later in what I say. It's very important to realize that everything we do in physics is really in terms of vector spaces. The transformations are in terms of matrices. The gravitation, electromagnetic fields provide a complementary system of associated fields and waves. We assume that no measurement here in classical physics interferes with any other measurement. Now we get to quantum theory. In quantum theory, observables are known to have these interference properties. That A times B is not the same as B times A. If I take an empty cup and I pour coffee in it and then tilt it upside down, that's different from tilting it upside down and back and then putting the coffee in. The state of a system is given by a vector in this metric space. And therefore, this metric space must be a representation space of the algebras that form this Lie algebra, these operators. If you stop and think about it, what I've got on the board here is an incredibly powerful foundation for physics. I mean, it's not due to me, it's due to everyone, and this is what we do. We say we've got a set of observables, and what we'd like to find are a complete set of things we can measure. Position, momentum, angular momentum, spin, hypercharge, strangeness, charm, everything else. And when we find those, if we know the right commutation rules, we can say, let's find all metric spaces which support representations. That would be reality. So you might say that these observables are things that can be done. This is the hitting, the pouring, the moving, the looking at. These are actions. And the actions are represented by operators that form a Lie algebra. The things that exist, the electrons, the coffee, the human beings, are the vectors in this other space, the Hilbert space. Therefore, that which exists must form a representation space for the actions that can occur. We know a lot about how to do that, but we don't know how to do it perfectly. Many particle system is described by these vectors. Of course, now we know that because we can create and annihilate particles, we can use a creation annihilation operators. The state vectors also, of course, must support TCP. Now we get to the point where I began. These are the questions that have really bothered me most of my life, and I want to run through them. And my talk today will be to address each one of these 8, and they'll be numbered so you'll know where I am as we go along. What are the fundamental observables, and how are they related in a relativistic quantum theory? What is information and entropy? How do we understand diffusion in the era of time? How can we order information? How can we get order? And how does that emerge out of the second law? And the second law says things are materials. Yet we're living. We are systems that somehow or another, complex as we are, we manage to fight against entropy. How can we do that? How can uncertain information be best represented mathematically? How can we take numerical uncertainty? Because no one has ever measured a real number. It's never been done. You'd have to have infinite information. You couldn't store it in the entire universe. What are networks and how can we understand them? Is there a better way to represent data structures? We know about relational databases. We know about XML structures. So we're going to talk about new ways to represent data. What is the truth? I mean that in the most general philosophical sense. What is truth? What is the truth? How do we find it? And I'm going to use that to talk about a new type of game theory. And I'm going to take that game theory and I'm going to apply it to ways that we could do teaching and things that are new and different. What is measurement of an observable and how is that related to entanglement? So the last thing I'm going to end up with is a little bit of talk about touching on something that's close to string theory. So this will be a lot to cover. And I'm not presenting everything that I've done. I've done a lot of junk and I've just pushed that aside and that's not here. Maybe some junk here, I don't know. So let's start with number one. This really starts with my PhD thesis. What are the fundamental observables and how they're related? We of course know about the Heisenberg algebra. This is a Lie algebra. X and P commutators equal to I. And we can say, what is I? It turns out that I has a spectrum from plus infinity to minus infinity of any real, or if you make these Hermitian operators, any imaginary number. So this is really, this has a spectral value of I times some real number. And it turns out that classical mechanics really thought that that was zero. In other words, position and momentum would commute. But in fact, we found out that there's one value it can assume in the universe that we know it, and that's Planck's constant divided by 2 pi times I to make these two Hermitian. Then we have these operators. These are other observables in our Lie algebra. They're our rotations. They're a symmetry group. And then if we add the symmetry group to the momentum operators in relativity, that's 3 momenta and the energy operator, we get what is called the Poincare algebra. If you take that and exponentiate it, you get the Poincare group. And what I did for my thesis was I extended that to a 15-parameter Lie algebra that in fact adds relativistic position operators and becomes a foundational algebra for quantum theory. Now you get some really nice results and you can close that off with your TCP operations and it serves as a great foundation for one-particle descriptions. It turns out that you have to use a proper time theory for that. And the proper time theory is just difficult with multiple particles. And I knew that very early on. And so what you do is you can use this algebra to find good particle representations group-wise. It's a lot better than using the Lorentz group or the Poincare group. And then you use those representations, and then you forget where you came from and go on. So it's a beautiful group theory basis for particles and much easier to use than that. This is the algebraic structure, and that's what I did for my PhD thesis. And the general state of a system is represented by Planck's constant. We often forget because we just assume that that's there. Planck's constant, the value of the energy in magnitude, the sign of the energy, that should be an epsilon, momentum, 3 momentum, B0 and B1 are Casimir operators of your internal spin group, which allows multiple spin representations, your spin, your sigma, and all of your internal symmetries that are added into that too. So that's the space. Now one nice thing that I was able to do with that Lie algebra was many of you in studying quantum theory are familiar with what is called the Foley-Wolfhausen transformation. For those who know how to pronounce it better, I think that's close enough, isn't it? Wolfhausen. Anyway, what it is in the Heisenberg representation, you're looking for a way that the operators in quantum theory look like classical operators. And so what I was able to do here was something that was very interesting. It's an extension of Gell-Mann and some other work that tried to find how do you find classical looking equations in it with a spin 1/2 particle, a Dirac particle, and an electromagnetic field, and make it look nice in that representation. And I was able to do that. And here are the free equations. This is what you have. And of course, this is your Hamiltonian gamma mu p mu. And of course, the commutator with that gives the dot product, and that's of course with respect to proper time. These are really nice equations. This is the spin, this is the orbital angular momentum. They add up to give you your total angular momentum. And this is just the free particle, which doesn't tell you a whole lot. Now, if you add charge to the particle and you say, how do I do that? Well, I think one of the best things that I've done in my life was to figure out how to do this particular set of equations in a closed form, because there are many of these operators that only close when they're in infinite series. They're very difficult to get closure on. And the way I was able to do that was I took H, the Hamiltonian gamma dot P, and I anti-commuted it with these operators. And when you do that, you get a form on the right-hand side, even though I'm using the dot product there. In other words, this is like mass times velocity would be equal to 2 times d mu. That's because I've got h times x plus x times h. And that would be twice d mu. And you're familiar with d mu from your relativistic theories. It's p mu plus e over, or minus e over c a mu. That's what we're talking about here. So it's your covariant momentum. And then here it is with the F mu nu, which is the electromagnetic field. And it would be interesting to look at this, you know, with other types of vector fields, like with interactions and so forth, and see to what extent systems like this close under more general fields when they have mass and how that alters the equations. Here's the time derivative of the spin and so forth. So it really gives a beautiful set of classical equations. And then the next thing I did in my life is I started looking for some extensions of this to explain internal symmetries. I found a very interesting regularity. All of these things, these are, the last three were all published in PhysRev, and this is published in PhysRev. And this was an interesting regularity in the hadron mass spectra. It could have been a fifth force. But when I looked at it, when more data came out, it turns out it didn't extend the way I thought it would to higher dimensional representations. So I kind of abandoned that for a while. We know, of course, what these internal symmetries come from, but still, it looked like there was another mass relationship that no one has ever been able to explain. So I started rethinking where I was going in life and what I could do. I couldn't do a many particle proper time thing with my groups. I wasn't, after working for several years, I couldn't really bring the internal symmetries in a way that I thought was non-phenomenological. So my direction changed to consider what it meant to measure an observable meaning of information. I was already bothered by the lack of exactness in position and momentum, which are really impossible to measure. And yet we assume with our Lie algebra that we can measure an exact position state and an exact momentum state. Neither are possible. If you try to look at the position of a particle, then you create another particle when you get inside its Compton wavelength. Therefore, it's meaningless to say you measure something more accurately than its Compton wavelength. We live in a universe that has finite extension. There's no such thing as a plane wave. We know where that particle is. It's in this universe. And therefore, the wave is localized to within, you know, our universe. And so these kind of things bothered me, and I was also bothered by our number system. And the fact that I really believe that if we could have a closed form for error in our number system, an augmentation of the real numbers, that we could understand measurement theory better. Well, the next thing I did was probably the most exciting thing, or one of the 2 or 3 most exciting things I've done in my life. I was trying to figure out information and entropy, and I was looking at diffusion. And I knew that information measured order, negative energy, entropy measured disorder. And disorder can be studied with a random walk of Einstein or by diffusion of Markov. If we look at what Einstein did, some kind of echo there. Then, of course, Einstein, as you know, studied Brownian motion, and this was a real incredible thing he did in 1905. 1906, Markov studied the matrices that gave transformations on diffusion. Diffusion is a loss of information. We studied in classical physics. It's like when you spill the red wine on your new rug or something like that. It's the irretrievableness that gives us our arrow of time. And why that's very important and why I became so interested in entropy, information, and the algebras associated with disorder, I'll talk about right now. First of all, I want to give you an example of a Markov matrix, because it's not something that everybody studies all the time. You may have come across it and may not. And here's a matrix, if you imagine the big parentheses out here. And you'll notice I've got a diagonal here that's 0.8, and I've got a 0.1 up here and a 0.1 here. What I'm really meaning by that is imagine you're on a line in one dimension, and I have an 80% probability of staying where I am, and a 10% probability of moving to the right, and a 10% probability of moving to the left. That's what this transformation will do for you. That is a Markov transformation. And you'll notice that it will not have an inverse. It diffuses you out. And you can't get an inverse from this because if you do, you'll end up with something that invokes negative probability. So it's like a violation of unitarity. You'll notice that these sum to 1. That must be true. So a Markov matrix is a matrix such that the columns always sum to 1 and they have no negative elements. They can have 0 elements, and all these elements out here are 0. And so that gives us a Markov matrix. If we want to study diffusion, that's one way to do it. The thing that I did was I studied the general linear group. And as you're aware, the general linear group is the non-singular linear transformations in n dimensions. It includes the Poincare group, the Lorentz group, every other group that you can imagine is all in there in the general linear group. So it's a Pandora's box of things, and it's not even totally solved, I don't believe, mathematically, as to finding all representations and all decompositions. And I was able to look, I was looking for the diffusion process. Is there a way to make a Markov transformation like a Lie group? Of course, it doesn't have an inverse. That is called, a group without an inverse is called a monoid. And what I was able to do is I thought of something very simple. If you have two people and you talk about diffusion, one way you can talk about it is you talk about giving each other some money. So I've got some money with me right now, and you have some money. If I give you half of my money and you give me half of yours, every minute, and we do it again and again and again, that's a diffusion process. It's called rob Peter to pay Paul. And I'd rather rob you than pay me, but anyway, that's a diffusion. You can see how you end up. If it's 50-50, 50%, 50%, you end up with the same amount of money. And after you have reached equilibrium, you can't undo it to know who had how much money in the end. That's the era of time. It's just like the wine in the road. Okay, so how could you represent that as a Lie algebra, as an infinitesimal transformation? And the answer I came up with was rob Peter, pay Paul. And the way you do it is right here. This transfers an infinitesimal amount from this ij should be upper right here, infinitesimal amount from this I and j, and it transfers it from this I to this j. And you always put a -1 on the diagonal. So I'm going to imagine matrices that have a 1 off the diagonal anywhere, and a -1 on the diagonal that matches it so that the sum at the bottom is 0. Now, for those of you who think about it real quickly, if I exponentiate e to the alpha times this matrix, the first element in that expansion is a 1. And the 1 has 1, 1, 1, 1, 1, 1. So that takes up the 1 in the Markov process. Therefore, these things are going to be 0. And it turns out that in order for this to work, every power of this matrix right here has to be such that the sum of the column elements in every column is 0, and that works. And these form a closed Lie algebra. And it's what I call a mark. In other words, if I take a 1 in all the positions off the diagonal, here and here, put a -1 corresponding to them, end up with how many? N squared minus n elements, and that forms a Lie algebra, and it closes. And I don't think anybody's ever studied it. You don't study it because diffusion is not a group. It's not normally thought of that way. And so, although diffusion has no inverse, I studied it from that point of view, and then I was able to show that the general linear group, every linear transformation that existed, is a Markov-type transformation, plus one of the diagonal transformations that just gives you scale. Like this axis is twice as great, a third as great, or whatever. And this gave me insight into irreversibility, but it didn't really explain the information. The Lie algebras and Lie groups were now connected to Markov theory. In other words, there's a vast information and power mathematically associated with Lie groups and Lie algebras. We now have them connected with all of diffusion and Markov theory. So anytime you can connect two branches like that, it's very important. I mean, I thought it was important. Now, how can order emerge? This is the third topic now. In view of the second law, we all know the second law of thermodynamics. How is it possible to do that? Is it possible to do it in a linear way? Well, I attended a talk in 1991 on Fibonacci numbers, and it got me thinking about this, and I suspected that those numbers represented some kind of natural law in nature. Why is that? It turns out that Fibonacci numbers are seen in a vast number of things that are alive, flowers and all kinds of things. Never mind the fact that we like cereal boxes that have that ratio and so forth. Fibonacci originally was very interested, you need to read a history of him if you never have. He was living in the 1200s, and he followed his father around, who was a merchant, and learned all these things from India in the Near East and brought them back to Europe, and they thought he was a genius. What did he bring back? The Arabic numbering system, and he brought back algebra. And it was just absolutely incredible. He went to kings after that and showed them how to, solve simple equations. Well, he was looking at population. And rather than just coming up with the numbers, he had actually a vector. In his vector, he was looking at populations of rabbits. He assumed his rabbits didn't die. And you had some old rabbits and you had some new rabbits. And so imagine now a vector that has two parts, X and Y, and representing the old rabbits and the new rabbits. And what I did was I said, well, what if we looked at the general linear group acting on that pair? Is it possible to generate the transformations that would get us to Fibonacci numbers? So I studied that a lot, and I looked at these various motions. Then I quantized the classical system. Why is that? Because I know the general linear group has diffusion in it. So there's the second law. Is it possible for the other transformations that exist, namely the scaling, and in particular the unequal scaling, which has to do with unequal growth, like sunshine coming here and our heat going out into cold space there, unequal growth in systems, to counteract that and leave us with a system that had a constant amount of information? Turns out that there is, and you can find infinite number of solutions to that. However, I was able to prove that the Fibonacci sequence is the simplest quantized linear system that preserves information while you are having diffusion. Now, when I did that, I also found the differential equations for the generalized functions for the Fibonacci sequence. I was able to take the Fibonacci numbers and find the interpolating functions for that, find the generating functions for that. And just like the gamma function, does the factorial, it was the same type of work, the differential equations and so forth. And so that also opened the question of why quantization occurs. Quantization, I'm talking about a classical system here. If you look at a tree will grow up, and it doesn't just grow up and produce one huge leaf, does it? You ever thought about that? What it does, it grows up and it puts off a branch. One, two. Then that branch, when it's old enough, puts off another one, and then this one will put off another one because it's old enough. So you get 1, 2, 3, 5, 8. You get the whole Fibonacci sequence if you look at the limbs of a tree in the end. Why does it do that? I'll let you think about that. Why we don't end up with just one huge leaf off of a plant or something. But if you look at them, this is what you get. You get these Fibonacci sequences. Now, how can uncertain numbers be represented? Most of you have heard my past talks, and so if you feel sleepy, feel free to get up and go back and have another piece of pizza or sandwich or whatever. If you had to listen to this, any of this again, I thought you at least should be fed properly. I was sitting on Saturday, on the 19th of March, this day, in the year 2000, in my kitchen. It was quiet in there, and I was looking at these Markov processes, and at the same time, I was thinking about how we deal with uncertain information. And I had the idea that the ones and zeros weren't working as probabilities. If you take probabilities and try to make something mathematical out of them, they just don't form a nice mathematical structure. They only do when they're part of a system. And so what I did was I said, what if we looked at this lowest dimensional representation of the Markov algebra, which is an x1 and x0. Remember, their sum is preserved because we have a rock, Peter, PayPal, and we're diffusing the information. And so therefore you can normalize those and treat them as probabilities, and then they add up to 1. If we took that vector and said this is the probability to be true, the probability to be false, we could represent a 1 over a 0 as a 1, a 0 over 1 as a 0, and we have a continuous set of things in between. This, of course, for those of you who have thought about it, should be very reminiscent of what we're looking for in quantum computing, where we're using spins of particles that spin up and spin down, but not classical particles. But when we're talking about information that's already known, we're not allowed to have interference in these systems. So we're looking at error in things that exist already. So I said, let's look at the Markov representation as a generalization of the 1 and 0 and see what we can do with that. Therefore, my suggestion is what? Probabilities should never be treated as a scalar. Never. Only as a vector. We do that in quantum mechanics already. We use a distribution function like psi of x, and it has all the different parts of that vector in it. We don't just say some probability. We always have the probability of the thing and the thing in other states, so like not the thing. That's my point that I'm making. So I took that and took these objects and I built a new kind of object which had two components. I called it a bit vector or a bitter, similar to a spinner. I was able to show that the Boolean truth tables using a constant set of constants, there's actually 16 of these constants where alpha goes from 0 to 15 for all the different logic operations that exist. And you can smoothly go between all of those with this structure, and it closes. In other words, you can't get probabilities to close like this, but if you have vectors of probability, not probability, then in fact, the products of those probabilities give you a new probability. And so you have a new thing that's not dissimilar from these other products that we've had, like the scalar product with the linear vector space, or the commutator, which gives us the Lie algebra. Then I generalize numbers as outer products of these, just like we take a binary number as 1011.101. These are now vectors, and so I generalized all binary numbers as these outer products of Markov representations. So I end up with something kind of strange here. Now what I see is I see numbers as being representations of a Lie group. It's actually not a group, it doesn't have an inverse. It's a Lie monoid. It's a group with everything but not an inverse. So you can have diffusion. You can take that Egyptian stone with the thing where the farmer had so much rice that he gave to someone in order to pay him to lift the stone up, and you can say, oh, he gave him how many? It's 113 point, can't read that number, 73 bushels of rice for he and his family to do that. And so that's a digit that has become erroneous, just like the ones and zeros. And so you can represent error in all of its forms with that. It turns out that Rayleigh second-order entropy is a natural object in that algebraic structure. If you take the logarithm, the rebuilding of all the arithmetic operations has been done smoothly. One hope is we can automatically manage uncertainty in computers. In other words, what I envision there is all of our tables have these errors built in, and now when we put these into something, we have an exact mathematical algorithm that manages those errors, and in a particular sense, it might even replace your Monte Carlo processes by doing a horrible calculation once, where it's really doing all the mathematics of those probabilities that go in all the different ways in the detector, so you don't have to route the particle 1,000 times. I just published this. It was published in Italy in a conference there. It was refereed. And I have a patent on that. It was awarded the year before last. So I'm very excited about that. The question is how to take that and do something with it. But it's very interesting just from the point of physics. Because now we have operators that are Lie algebra acting upon vectors in a Hilbert space and giving not numbers, but representations of another group. What are they? The Markov group, where you can lose information and measure information and talk about the measurement process. Fundamental operation, if you're just using this for a computer, of course, is if x is greater than y, then do this, else do this. It invokes a bifurcation in the system. And now what we're going to do is, remember, if we have numbers that are these fuzzy numbers or uncertain numbers at the end, it's possible for them to overlap. In fact, you can treat them as functions. And these new numbers I actually was able to show about a year ago when I was doing this work on these numbers. You can actually show that they're distributions. And therefore, these distributions have scalar product. So this new kind of number, you can actually take a scalar product with something else, like folding two functions together that are properly normalized. And the main thing is if they are overlapping to some extent, there's a certain probability is x greater than y, and there's a certain probability of else. That means you have to do two things at once, and this is how our brain works. Our brain works by going two ways at the same time. We say, oh, I'm going to do this. No, well, I have a certain probability to do this. If I do this, I can't park there, da, da, da. And our brain works like this. This would give our computers almost the same thing that we do in physics with an A dagger and an A. creating and annihilating these processes. Why do we have to annihilate them? Because we start out with one program, one thread in the computer. It then bifurcates, those bifurcate, those bifurcate. At some point, we've got to kill these processes because they're not going to produce anything. The probability of them is so low. So those processes die out. And so I've worked a lot on how you build this into the computing system. We've done overloading of operators. I've worked with an engineer, actually in electrical engineering on this, and she was the one that presented the paper in Italy for us, and we did that as a joint paper. What are networks? I told you it'd be kind of fast, but it's a survey. And all the papers that pertain to this are in fact in this book down here. I'll leave this with the department along with the videotape or DVD of this talk. It's not meant to be exhaustive, it's just to give a kind of a broad overview. Give you a moment to breathe. What are networks? Networks are really different animals. And Vladimir Goodkoff, Dr. Goodkoff and I became very interested in these. I was able to get a grant, it's the nicest grant I've ever had, $2.5 million in total funding from DARPA to study networks. And that really got me going on these things. And I was at one of the DARPA meetings, and a guy stood up and he was giving this horribly dull talk on Linux kernels and things that can go wrong with security, because it's, they're funded by the military. And so I'm sitting there thinking, what am I going to do? I've got to sit here. There are only 25 people. If one leaves, they know who you are. You might lose your money. So I'm sitting there, and he said, before I begin, I want you to know that mathematics is the most that networks are the most complicated things, or one of the most complicated things mathematically. No one understands networks. They're just not classified, organized, and understood. So I started thinking about them. What can we do about them? Well, a networks is obviously described by a matrix, and what do they encompass? They encompass your power grids, your transportation networks, your neural networks, your lymph system in your body, your communications, your internet, your phone. Of course, DARPA was interested in internet and security violations, and that's what we were all studying. Financial networks. Well, we proved that physicists can't solve financial networks. It doesn't matter how many quants you take up there, and they quit studying, renormalized quantum dynamics or something, and go up there and start dealing with these things. I don't think that those they did too well with that. But networks are incredibly complicated. Just as soon as you think you understand them, you realize that the topology is as complicated as things be. It's a set of points with connections among some of them. And the connections can be different weights. Impossible. Topologies that are exceptional complexity and difficulty. In fact, they can be represented by a matrix, Cij. That's the connection between node I and node J. Now, obviously, you could have a continuous set of these things, but we don't really need to jump there yet. Let's just imagine you have a finite number of things, like all of the airports in the United States that have a 3-letter designation. Let's list them out. I equal 1 to however many that is. And whether flights, the number of passengers taken from one airport to another, Cij, is going to be a positive number. So what we're studying when we study networks, there are matrices that are square, that have positive numbers off the diagonal or 0, and whose diagonal is not defined. Because it doesn't make any sense to talk about flying from the Columbia Airport to the Columbia Airport. So the diagonal is meaningless. So that's one of the problems in looking at this mathematical problem. You're looking at things that are bounded. It's almost like one of the simplex problems, where you have something bounded by constraints or things like that, and so you don't really know how to deal with it. However, what I was able to show was that the Cij, if you set that diagonal equal to the sum of the off-diagonal pieces in that column, the negative. In other words, I take up the matrix, the connection matrix, I add up all those positive numbers in a given column, take that total, put a minus on it, and put it in the diagonal. That becomes a unique matrix. That matrix is an element of the Markov-Lie monoid, or Lie algebra. And in fact, what I was able to show is that there's a one-to-one correspondence between the two. Every network exactly determines a set of Markov transformations analogous to diffusion among the nodes at the rate of diffusion. And now we have connected all possible continuous Markov transformations in a one-to-one pattern with every topology that can exist on a network. So now we have network theory over here, any network. And I'm talking here social networks, Facebook, internets, communications, military transmissions, whatever, over here, connected to Markov matrices, which are connected to Lie groups. And there's a smooth transition between all of these, so we use the power in one of those to now study the others. So we've connected those three branches of mathematics, results in one can be used in another. And this allowed us to, since I can now take a network, if you give me a social network, or you give me a set of flights from all the cities in Colombia, or anything like that, any form of network, I can instantly derive by fixing the diagonal and exponentiating it, doing a couple of other things that normalize its size to make it more manageable, then I will get a Markov transformation. Since it's a Markov transformation, I know that the sum of the elements in a column sums to 1. Therefore, it's a probability. If it's a probability, I can now define entropy on that probability. So I can use Shannon entropy, I can use any other type, like I prefer to use Rainy entropy. You can use any of the Rainy entropies, generalized entropies on that, and look at those. But since one node is just like another one, they're arbitrary, I sorted them in order, and that's another result I had. Sort these in order, and you end up with an entropy spectrum of that network that's rather unique. And so there are ways to classify networks. And so my main result for DARPA was, if you have a network like a military communication system, we don't know, we can't predict what the entropy spectra should be. But what we can do is measure it. And everybody says, hey Bob, is this thing looking like it's working right? Great. Is it still looking like it? And next day, is it still working? Yeah, everything's normal. So we get to a sense of what is normal, then we look for aberrations in the spectrum. How does it shift? Then we have software written in Java that immediately goes in, you click on the curve at that point, and it shows you all the nodes that are giving you problems. And we use that to identify things at universities I won't name, where students were in the dorms using it to sell things, and pornography and movies and all kinds of other things. It wasn't at this university. It was just kind of interesting. We were able to show that. Next topic, number 6. Doing fairly well. I don't know what slide this is. Is there a better way to represent data structures? Well, in order to do a lot of this stuff, I did a lot of junk work. It's the kind of stuff that all of you are very familiar with what I do. I have a group of people, and we do databases, and we do, weird stuff, like the jail system or the emergency management system for the state. But we had a lot of people that could work with me then and do a lot of programming. And that was the way I was able to bring in some money and get some indirect costs and so forth, which was very helpful. In the process of doing that, it kept bothering me that databases are designed the way they are. I don't know if you know this, but Larry Ellison, who invented Oracle software, the relational database, it was an IBM product that he stole. He was working for the Internal Revenue Service, and as a very young guy, just out of computer science school, and he started looking at this, and IBM was testing a relational database, which was made up of these tables, these complex joins. And so IBM didn't have any patents on it or anything. He went off and founded Oracle, which, as you know, he's one of the richest men in the world now, which is pretty impressive. And therefore, relational databases, which are incredibly difficult to maintain and expensive, you have to have a computer scientist to make sure that these joins are reached up to what is called fifth order normalization, so that data is only entered once or something like that. Very complicated kind of things. The problem is if you take regular people, like us, we're regular people, we're secretaries, or all the regular non-computer science people, we can use Word, we can use PowerPoint, we can use Excel spreadsheets, we use Mathematica, but we can't build good databases. It really requires somebody who's really good to sit down and do something like building the relational database for the university's grading system. It takes people who are really experts to do that. And I don't have time to tell you why, except that relational databases are very complex. And so you just got to go to school a long time to learn how to do it. It's kind of like accounting. There's another kind of database that has emerged since the web. It's called XML, Extensible Markup Language. It's very flexible. It's a hierarchical system. You might say people and under people, or locations and under locations, or buildings and under buildings, or utilities and under utilities, something else. You can have all of this, but it turns out that although they're very easy to build and everything, the flexibility and the lack of structure does something horrible. In order to find Joe Johnson in such a database, you start at the first record and look at everything in there. There are no special methods that let you fork out in these special trees in order to find the data you want. So what I've done is I have worked for several years now, I guess about 6 years. In the background, I built a new kind of database, and it's a hybrid between XML and the relational database model. And it uses pieces of both. It uses a concept of information structures that are like informational structures like Lego blocks. And they're connected by pairs of relationships, and it makes that database a network. Ta-da, back to the networks again. Our work resembles the new research, if you're familiar with it, on the semantic web that's being done by Tim Berners-Lee. There's a tremendous amount of work that's going on right now on networks, in particular like the internet, to take the entire language structure and be able to put it into a network type of thing. And that's what they're working on. In other words, where every verb and every consonant and everything has a place in this complicated network. Let's go very slow. This is like a simplified version of that that works right now. And here's an example. Here's how you build. I want to show you how you actually build one. Do a /p, because a person is one of these informational units. So I do /p, first name Joe, last name Johnson. You notice the abbreviations. Start a location. Relationship of this module to the one above it. In other words, the modifier. Works at. Place, USC. And under that place, I've got a communications module. And I have the relationship is my work contact. There's my phone, there's my web address, and in the other one, oh, I forgot to put my social security number in. So I can go back and put my social security number in that, close it out. I can add variables, take variables away, create tables, and I do all of this on the fly. We can teach somebody to build incredibly complicated network structures in less than an hour. And of course, what we do is we build this, and it's built on Oracle using a network of Oracle modules. And I have a patent pending on this right now. New database has the advantage of going to build a database now, and instruction fields can be added and removed at will, which you can't do with another one. You leave these things called orphan records. An icon click, the system will build a relational database for you. You click one button, it'll build the entire relational database out of that network structure, or it will also build an XML database. Therefore, I suggest our fundamental information databases should be networks of fixed information units. Complex information is thus a network or Markov reality with weighted links. I'll tell you, I have a grant application in to study this, and rather than going to the NSF, which my chances would be like 1 in 500 or something like that, to maybe get $60,000, I've applied for a very substantial sum that will look at, relatively confidentially, I don't want you to discuss this with everybody. We have a proposal in, we'll know in June if we get this, to build a network of information for the criminal justice system for Richland County and then outwards in other counties and finally for the state that looks at gangs and how gangs have people that are related to one another and how cars are found. So it's not just gang members that are related, it's where cars are found or gangs do drugs. And so it's a very complex network that will have dialable weights of modification among them.
Then gangs in Richmond?
Yeah, oh yeah. In fact, last night I had information from someone who was an undercover person in gangs that they were going to have an initiation, and I think they didn't do it. But the people who were initiated were supposed to kill a woman in one of the Walmart places, but the police intelligence didn't know where it was. That was to occur last night. I didn't see it in the newspaper, so I guess it didn't occur. You know, we have a lot of gangs here. So this would be a way you match gang graffiti with locations with cars that are abandoned, cars with drugs that are found in them, and it forms a complex network. And what you want to do is do what we do intelligently anyway. is to take these Markov things and expand them out automatically with our processes by exponentiation and ferret out the connections. And we'll be able to say, when we finish with this in a year, if we got the money we're asking for, which is quite considerable, about $500,000. So if we get that amount of money, we'll be able to say cocaine, and it will list all the people in Florida, in Richland County, of how closely they're connected with cocaine. Anyway, just thought that would be an interesting, I'm trying to do some real things as well as some things like this. I wouldn't want that mentioned outside the window.
Mention what? I didn't hear it.
A new type of game theory. I want to remind you here of, this is something that always fascinated me when I was an undergraduate. I picked up a book on game theory which was done at the Rand Corporation. And as you know, game theory was done by von Neumann, who was working in the mid-40s, actually a little bit before that, published a book on the theory of games and economic behavior. It was really quite remarkable. It's a whole new branch of mathematics, and he tried to understand all games and build a mathematical infrastructure that would handle it. And I went up and I was presenting my work on networks at MIT Conference on Complex Systems, and John Nash gave the invited dinner speech. It was kind of strange because at the table were his wife and his mistress and his children.
That was game theory.
That was on game theory. That's real game theory. In fact, he fell off the stage. You know how scientists do this kind of stuff? He got so excited at one point, he's backing up, and everybody's saying, everybody wanted to say, "Don't back up anymore!" And there he went off, falling off the stage into the screen and so forth. What he really talked about was he has 6 PhDs at Princeton working with him using Mathematica to try to solve a 3-person game, in general, formula, where any 2 of them can form an alliance against the third. And they haven't been able to solve it for several years. When he said that, and many people think there have only been 2 papers written in game theory. One was by von Neumann, the other one was by John Nash, who got the Nobel Prize for that, called Nash Equilibrium. He did that when he was about 21, 22 years old. So you guys better get busy for graduate students. And I was thinking there, you know, I already know there are extreme difficulties with in-person games. If you look at a 2-person game, it's in 2 dimensions. A 5-person game is in 5 dimensions. And if they're not zero-sum games, you certainly can't solve them. And even worse, how do you even assign the payoff matrix? And no one can solve any collusion. So if you look at oil companies and different countries that are partnering, oh my dear boy, I said I was going to partner with him, but if you and I set the price of oil at so-and-so, how do you solve it? How do you do anything like that? How do you even fill in the matrix with the payoff numbers being as dynamic as they are? I think I thought of a way to do it. Let me remind you of a 2-person game, standard binomial theory. Frank is going to choose A or B over there, and I choose 1, 2, or 3. If it's a positive number, I pay Frank. If it's a negative number, he pays me. So I'm not going to choose 3, because if he chooses A, I pay him $5. Here I pay him $2. I'm going to lose anyway here. Of course, what game theory is once somebody puts these matrices in place, find the saddle points, optimization, payoffs, and everything else. Now, I had done some work way back in 1984. Robert remembers it, with a classroom where I designed an algorithm where the students would vote with expert opinion. The computer would learn who the smart students were, and the computer would figure out the answers to questions. And I had this algorithm that was a couple set of nonlinear equations, and I've given a talk on it before, so I won't go into it here. But I was thinking about that, and I thought, golly, what if we took that system of expert analysis and used it as the basis for an automatic dynamic determination of the payoff matrix in game theory? It would solve the in-person, it would solve the collusion, it solves everything. So the questions are posed. It's a different type. It's a sub-game of the von Neumann game. You pose questions to people. And I just gave a talk at the University of Utah on this for petroleum. And the people there were petroleum experts. And they're trying to decide, do we drill here? It will cost, well, how much will it cost? So you ask them maybe 20 or 30 questions first. You find out, the computer learns how smart they are in answering known questions. What is the truth? What is the answer? answer is the answer that's most in the middle for those people weighted in proportion to how smart they are. How smart are you? How close you can come to the middle. That's why it's two coupled nonlinear equations. So anyway, they have to have one word or one number answers, and then someone gets paid for the right answers. And the probability that the person is right and the probability that each response is right are coupled. And the payoff is automatically determined using information theory. It turns out it's the logic function, which is P over 1 minus P, that gives you the proper weightings of these, and you can show that that is the thing you use to vote. Now, the algorithm is actually more complex than that because you have some learning and some things over time. So I presented that the next year, which was last year, at the next MIT conference, and I've applied for a patent on the design of this new game theory. I gave a seminar at the University of Utah. We plan to apply that for expert consensus on how you vote for investments. And I think we can do better than the current system, although I'm not going to put my money in it yet. Petroleum mining, medical decisions. Do we operate on this sucker or not? You know, what do we do? Well, get 5 surgeons there. I wouldn't operate. I wouldn't do that if that were my brother. You know, they vote in a certain sense. And you determine by the overlap. What you're really doing here is you're trying to capture the subconscious information that people have, the judgment that they have, that you can't put in the program. So you marry the mathematics and the computerization with this judgment that people have. The system learns who are smart. You learn what is true. Can the game theory, this is 7 prime, can this game theory improve education? Well, as you know, I've given a talk on this. My talk on that didn't go right because our little devices didn't work. Can we use this to improve education, where the students come into a class with a web-enabled device and they answer the questions, they log on. The system we have built will now take attendance, it'll grade their homework. You can ask a question, if it's one word or one number answer, it grades it all, it throws out the bad questions, it emails them an answer to the question at the end, and all you have to do is stand there and talk, give them information, ask questions. When you look down there, you can see all their wrong answers on the screen too. So it's really kind of neat. And so we're going to pursue this and see how well we can do something revolutionary with education with that. You can build demographic data, keep them all engaged. It's more like a one-on-one. So if all of you had such a device, I'd be able to ask you a question and see exactly whether you're paying attention or not, like on the definition of the Lie algebra or something like that. One aspect of the system is we're going to do some very interesting things. Again, no need to mention it other places. We would monitor keystroke rates along with error rates. So when Johnny has his keystroke rate slowing down, we would then know that maybe a gang was trying to get him to join, or his parents were getting a divorce, or you know, he was sick with flu, or his girlfriend left him and told him to go away and never come back. Something's wrong with Johnny, so it's a flag, because you can't type at the same rate without errors, and the system will monitor that. So it doesn't care how fast or slow you type, it's like in God. If you drop down a certain standard deviation below what you normally do in your fluctuations, the thing's going to flag you. It can measure all kinds of things like instructors' question quality, validity. We build an elaborate set of statistical analysis in the background that looks at this data and correlations between them.
Dr. Johnson, can we pause and let me change tapes?
Okay. This is the last thing that we have to do, number 8. And sorry about 3 minutes late, so I think I'll finish close to time.
Yeah, 49 years and 3 months.
Okay.
Okay. Number 8, what do we mean by the measurement of observance? This is really what I've been after all along. How does it relate to information and entanglement? What if our numbers are special cases of better numbers, and these are eigenvalues for quantum theory? It then means that our Markov-Lie group is a kind of third quantization on the system. Now, we all know that these better values are going to provide a fuzzy kind of quantization to things like our space-time. What is that going to mean? Well, the localization of particles, as you know it, really has been questioned for many, many years by many, many people. I'd say probably 50% of every physicist has said our theory of being able to measure the position of a particle, our theory of space-time when it's immersed with quantum theory, certainly as Pavel would say, when it's immersed with gravity and quantum theory, we have terrible problems. You get these quantum fluctuations, and the space begins to get all these violent upheavals and topological reconnections and things like this. And so things don't normalize. You have a problem with the renormalization. But certainly we know this, that uncertainty is bound by the Compton wavelength. I can't go and measure that thing inside its Compton wavelength. And the determination of any momentum is limited by the values because I'm in a box the size of the universe. You say, well, that's so big it doesn't matter. It does matter. Now I want to consider an eigenvalue, and you'll notice that I've done something very strange here. I put the x, the positions, and I put the momentums both in there as though we can measure them simultaneously. The answer is, with the bitter numbers, you can do this. How can you do it and not violate the Heisenberg uncertainty, which is the question I would ask at that point to your students. X here is going to be a whole set of these vectors going along here. P will be a whole set of vectors going along here of these ones and zeros and fractional numbers. But what happens is, if you think about it, h bar is 10 to the minus 34. So in the scientific international system, or even something, let's imagine we have something like the foot of a mosquito, something like 1/1,000,000th of a gram, something that's so small, like his toenail. Let's say